All right, one little point I want to make about lab 8, which is the gravimetric or precipitation analysis of the calcium chloride, okay? Oh, I'm sorry, the metal carbonate, whether you had sample A or B. My sample A's and B's are all mixed up, so don't look, whatever I said in class yesterday. But what's really cool about this is that these samples have some differences in them, okay? So I'm going to show you that in a second. So what I have here is a eraser that I almost dropped, okay? And that's what's blacking out the screen here. So I got an eraser. And I'm going to pour what says sample A here, okay? And I'm going to put this to the left side. And this is one of the things that always really was part of the things that I fell in love with chemistry, is to do all these pencil and paper things, and sometimes you're so far to left field with all the paper and math, but it actually math means something in the real world. That's what I love about science. We're not just out there thinking of something. It definitely applies and has applications. We may not know them, but so all the stuff we've been doing. So this is sample A, and all I'm doing is showing you the crystalline pattern. I'm pushing it to the left to get to the screen somewhere. Okay, wherever it might be. There we are. Oh, there's my finger. Okay, we can do this. No, we're getting too far. I was going the wrong way. Okay, so there is sample A in all of its glory. Okay, I'm not sure what kind of glory that could be, but we get there. All right, now let's get sample B. All right, sample B, I'm not lying, right? B, okay, and I'll put that off to the right. I'll just add some, and I'll just push it forward. We're starting to get it into the frame here. Okay.
How do we tell the difference?
Exactly. That's the point I'm trying to make here. The crystals that are made, I know it's like, wow, there's a tiny. Maybe I can move a couple of these. Okay. But these individual crystals, now of course these aren't individual formulas, but you should be able to see there's a clear difference in the size of the crystals. Okay, so for instance, these crystals here are smaller. These crystals here are bigger. Okay, and you may say, well, what's the difference? Well, what's cool about the bigger crystals are your potassium carbonates. And what do you know about your potassium? It's a bigger element, therefore a bigger ion. The sodium carbonates are much smaller. They're more finer. Why? Because it's probably a more compact unit cell with small sodium. So there it is. I mean, so if we were to do this again, you'd fail out and go again. Okay, pour out the crystals, and you could actually, I should have had you compare A and B to what you had. My bad. So the bigger crystals are the potassium carbonates. The smaller crystals are your sodium. So there's something to this microscopic world that leads into our macroscopic world. I find it to be very fascinating. Sorry if you don't. Okay, so in any case, rock on with the big bad self. Okay, now, that was from this morning's lecture. So I was helping you with the video I'll post to figure out what your chemical is using percent yield. Some of you guys are doing percent yield based on molecular mass or formula mass. That's not the right way to do it, as I'll say in the video. So without further frost, let's continue with this. Okay, I'm gonna get rid of this. Oh, all that work. Color coordinated, look at that. Told you I was stylish.
I can't believe you can see all those colors.
I can see red, blue, and black. That's a huge difference there. Don't give me a bunch of blue markers that have different shades. Okay, then I have some issues. Well, more issues than normal, okay? Okay. I'm honest about my issues. All right, now, so we left off with number 2, and we had this sodium carbonate, never seen that before, called washing soda, and calcium nitrate. And we talked about, just to revamp ourselves, what this was about, okay? And again, I really believe drawing what's happening. So what I said to you is I took 2 solutions. Sodium carbonate, aqueous, okay? Hey, -2 + 1, that +1 can't stick together. Group 1, ions are always soluble. And then, hey, we have calcium nitrate. Hey, we saw the calcium become a precipitate with the carbonate, but that's when the carbonate was -2 and that's +2. Hey, that's a -1 ion, table F and table E. So that's also going to be a free ion. You pour them together, and of course, these guys will find themselves, stick together, and be an insoluble precipitate. There it is, and then we write this as a formula, but it's really free sodium and free nitrates, Kardashian wedding. Okay, we would do this in Regents chemistry, but in real chemistry, and I say that not to be mean about Regents chemistry, because Regents chemistry is the New York State way of doing things, and some of the things that they require students to do is anywhere else in the world. This is crazy. But this is what we really write. We don't care about the sodium floating around and the nitrates. They don't do anything, they're just floating around. Okay? This is what actually happens. We get rid of the spectators. So this is the same what? Net ion reaction in this problem as you had in your lab. Okay. And what the question was this a redox reaction? And you need to understand, we're going from redox reactions to sometimes not redox reactions. Most reactions are, but you should realize that, hey, if this -2 finds this +2 and sticks together, there's no change of oxidation states. It's just a +2. Hey, I'm a -2 hooked up with this what? +1. You dissolve, water pulls me apart, and hey, there's a what? Hey, -2, I'm more attracted, and I stick together. I'm not exchanging electrons, I'm just going where I'm more attracted. Kind of like a bad male, okay? Now, so any case, it's not a redox reaction. The oxidation numbers are constant. They don't change. Now, this is the new part. Predict the KEQ. KEQ, okay, is nothing more than a way for us chemists or budding chemists, okay, I guess that's an asexual reproduction kind of thing, but any case, there's a chemist growing off me. Sorry. All right, stop it. All right, any case, sorry. Okay, KEQ has some synonyms. KC, KP, we'll talk about them, but I don't like the blue. I just lost my black, okay, which is hard because, there it is. And so it's equal to what? Generally speaking, the concentration of the products over the concentrations of the reactants, okay, to their coefficients, okay? And what's it tell me? Very simply, party people, if a reaction goes forward, here's my reactant becoming my product, and by the way, it's got to be a gas and or aqueous because those things have concentrations, molarities, right? Don't forget the brackets represents a M molarity. Okay? If a reaction goes to completion, which means it goes forward until we run out of something, we know that we're going to have a tremendous, tremendous high amount of products compared to reactants. Because the reactants are going to disappear. And that number is going to approach infinity. So you need to know that when you get a KEQ, or an equilibrium value that's a large number, you know it's a reaction that's going to completion. And we can do the same stoichiometry. If it's a number that's not huge, then it's not going completely forward. So if it's a small number, if KQ is a small number, that means when it reaches equilibrium, there are more reactants than products favored, right? A small number means that your denominator is bigger. And that means the reaction didn't go that much forward. But it did go forward by some amount. And that some amount is based upon the ratio still. So there's still stoichiometry here. I just want you to realize what is a completion reaction and what is one that is not completion. This, when you make an insoluble compound, that's a completion reaction. These ions have no ability to go in reverse because they're locked. There's nothing, it found a stable ion and water can't break it apart. Or, hey, a gas is made and the gas leaves. Okay, in the previous problem we had a what? A place where there was a enclosed, sealed, evacuated flask. Okay, moving on, sorry. And so we draw the picture. They love particle diagrams. What's missing? Hey, we poured calcium nitrate and sodium nitrate. They're both soluble. There's your solid calcium. But we forgot we have calcium +2 we had to draw because in the problem we added what? We added excess, right there, excess calcium nitrate. And so That's why we had to add the calcium. Okay, now we're off and running. Here we go. Here's our gravimetric analysis. Determine the moles of sodium carbonate in the original 50 milliliter solution. Who cares about the 50 milliliters? You added all of it. So how do we do this? Well, we have to have so we have the grams of our precipitate. And what do we know? Hey, 0.93 grams of calcium carbonate. Or guess what? Go into moles. That's so crazy. 1 mole of calcium carbonate is how many grams? 100! Now we're doing some stoichiometry. That's a fun one. You can't get in the door of the chemistry part if you don't know that one. Come on. Ew, whatever. Let's get even know calcium carbonate method mass was 100 grams. My God, what's disgusting, okay? What kind of family does he have? Okay. Okay, now. They don't do that in Riverhead, by the way. Did you see that family's tag? It's terrible. They can't spray paint on bridges as well as that other family. All right. All right. All right. And they did it so low on the bridge. You gotta be way up there and have people wondering how they do that. Okay. Sorry. All right, that's northern. That's actually not okay, we'll forget it. All right, so in any case, we get rid of the grams. Now, what do we know? For 1 calcium carbonate, there's 1 carbonate ion. Oh! And for every 1 carbonate ion, what are we after? What are we after? What are we after? Moles of sodium carbonate. How many carbonate ions are there in one of these compounds? Well, there's 3 O's, but there's 1 carbonate ion. All right, now if I wanted how many oxygen atoms, yeah, I would times it by 3, but I wanted how many of these singular -2 particles. Great question there. So it's a 1 to 1 to 1. Tough math here. Okay, so for 1 carbonate ion, I get 1 sodium carbonate. And some people said, what if I see this? Okay, what if I see this? Do I gotta write this out? No, but I'm just showing you how pretty it works out. So calcium carbonate goes bye-bye, and you're left with moles, and that's all they wanted. So really the math is 0.93 divided by 100. Okay? I think even I can handle that. Okay? And so the moles, of course, is 0.0093 moles of sodium carbonate. Okay? And that's an AP problem. Not a problem I made. Okay? But I hope you can see the labs that we do help you get this. Okay, G, the student realizes that the precipitate was not completely dry and claims that as a result, the calculated sodium carbonate molarity is too low. Do you agree or disagree? Now, molarity. What is molarity? It's big M, it's not fancy. Fancy M is molecular mass, pinky up when you write it. Molarity is moles over liter. So, if you're trying to calculate molarity, you would take the moles of your sodium carbonate and you would divide by the liter of solution. It was 50 milliliters, so it'd be 0.05 liters. I didn't ask you to do that, but certainly I would, or if I was writing a problem, I wouldn't do it like this easier, but they do it that way. The student realized the precipitate was not completely dry and claims that as a result, the molarity is too low. Do you agree with the student's claim? We agree that the molarity would be too low because there wasn't a completely dry. Now, think with me. Go backwards. If it wasn't completely dry, wouldn't some amount of this 0.93 be due to the water? Mm-hmm. Right. All right. So now we got to go read the problem again, just to make sure we got this. A student is given a 50 milliliter solution of an unknown concentration to determine the concentration of the solution. So they're trying to determine the concentration of the solution, even though they don't ask you to actually find the molarity. Okay? So what they're saying is it felt wet and damp, which means that part of this mass was due to water. Okay? So this is an over-evaluation. Okay? Right? That number's too high. All right, now, as a result, the calculated molarity is too low. Well, think with me. If this 0.93 is due to the calcium carbonate and the water didn't evaporate, isn't this an over-evaluated result? And if that's going to be an overvalued result, it's going to give you an overvalued moles of the sample. And if you solve for molarity, because the mole is on top, it's going to give you a larger molarity than expected, correct? So I would say no. And I would justify my answer by saying, if there was more water, okay, it's going to raise my, it's going to affect the amount, it's going to increase the amount of moles than expected, which increases the molarity because the moles are in the in the numerator. So there's many ways to say this concisely, but the bottom line is, if this has water in it, this value is too high. It should have been lower. And if it's too high, you're going to calculate more moles than you should. And because that mole is used in the molarity formula, you're going to calculate a larger molarity than expected. Okay? I'm not going to write that out, but something along those lines. They don't expect full sentences, but definitely make the leap from, hey, this includes water. This is too high, which is going to, this value is too high because you calculated from it, which means your molarity is too high because you used those moles, something along those lines. And you could actually, draw diagrams with a few words too there. But if you can see that, that's why I ask you to write a what? Conclusion. That's why I ask you to do error analysis, because they love to give you something like that. And by the end of the year, that's so easy. And that could have been easy anyway. All right, so moving on. Last little piece here. Student decides to determine the molarity. Ooh, there's something in my way there. Oh, my computer. What does that say?
There's a Zoom up There's a there. Zoom.
Oh, okay. How do you read that? My God, I'm like, I gotta go in there. I'm such an old person now. All right.
So I got the same.
Well, if you
number.
restart it,
Yeah.
I don't think they could stay on the Zoom meeting.
Oh,
Remind me
yeah,
later.
I like 11 last time.
Okay. All right. Student decides to determine the molarity of the same sodium carbonate using its second method. When the sodium carbonate is dissolved in water, CO3 negative 2 hydrolyzes to form HCO3 negative as shown below. Who cares? Don't say, I don't understand this. Don't worry about it. Okay, we're still early in the process. We haven't done acid-base reactions. It doesn't matter. They're giving it to you. These are just big ions. Here's an ion. It's carbonate ion. Here's water. Here's a new ion. Don't get intimidated by a chemical reaction you haven't seen. Step up to it and say, yo, what's up? What's up? In fact, if you have to, you can eat it. Or spit it out. Oh! All right. So, any case, here we go. And they gave you the key and Q. Oh! Products over reactants. Notice I didn't include water because water is a liquid. Liquids don't have a concentration. Solids and liquids do not apply. And look, here is the key to the problem. Is this a big number? Is that a big number? No. So that's telling me that I have more reactants than products. That tells me that this is not a completion reaction. It does not go forward until it stops. That's what I want you to pick up here. Okay? So draw a U diagram. Don't draw yourself. All right, with reactants and products include the KAQ. So, because KAQ is small, this is 100% reactants. This is 100% products. You don't have to draw. We should know the products are to the right, right? These are the products. These are the reactants. Okay, so we just do it like that. Now, here's my U diagram. I am favoring more reactants, so the K equilibrium position should be closer here. So it's not much of a U, it's more of like a bad V. And there's my KQ position, right there. At equilibrium, I favor more reactants. Why? This is important, people. If this is a line straight up, with that small what? That small value, that's telling me I barely do what? I barely go forward. I go forward a little bit. I do not go to completion.
That's all you have to draw?
That's all. That's it. Okay, when I was showing you these, I kept putting them in the middle. I was stretching that just so you can learn. Okay, that's all. That's it. It's about the concept. All right. In the original sodium carbonate solution, in equilibrium, is the concentration greater, less than, or equal to? Justify your answer. Okay. Is the concentration of the carbonate greater or equal to the CO2? to the HC. So how is this compared to that? So in the original sodium carbonate at equilibrium is the concentration of the bicarb ion, that's what they call the bicarb ion, just showing off. Is it greater or less than? Well, because it barely goes forward, the HCO3 negative is less than. Doesn't go forward. All right? So at equilibrium, it said at equilibrium, it's going to go right to more reactants. So we're going to have a lot more of these guys than these guys. So you could say that HCO3, which is a product, is going to be less than one of the products. And notice something. Aren't they 1-to-1 anyway? You have to make an adjustment there. Justify your answer. KQ is small. Small KQ means you're favoring the denominator. The denominator is the reactants. That's it, guys. I'm not asking you, okay, other than that, just understand what that means. We will derive this from thermodynamics, and I'll bring it back and be, okay? Maybe not all that. Okay, here we go. Equimolars samples of 3 gases. Brand new question. So now I have gases. Gases are solutions, and so are aqueous, right? So we can put the molarities. Or introduced to a container that is heated to 600 degrees Celsius. Who cares about temperature? But we have them are into an empty container. Okay, so here are the 3 gases. They are reaching equilibrium. Let's look at KQ. It's 50, or as we say in North Riverhead, 50. Okay, so it's 50. Is that huge? No, it's not really small either. Huge would be thousands. Okay, so if you're somewhere around 1 or 100, this is showing me a U diagram. That's probably something like this. More like that, right? So more down the middle. That'd be like 1 if a KQ was 1, but that's 50. So we know this doesn't go to completion, but because it's not less than 1, right? It does go forward somewhat. Okay, so according to the information above, which of the following will occur as the system approaches equilibrium? So what we have, okay, is we have these 3 gases. Now let's write that. We have H2. I'm not loving the green myself. H2. And we have A2. That makes one of the cool molecules, high, the high molecule. A happy chemist. What you making today? What are you making today in the lab? We're making high. All right. I'm sorry. I've got issues, you know it. Okay. I didn't ask if you're getting. I said you're making it. Okay, so don't confuse that. All right. What's so funny? This could be a lab in Denver. Or an elevated lab that rises up. Okay, what are you guys laughing at? Okay. All right. Now. All right, so what do we got? According to the information above, which of the following will occur? Well, they said equimolar, right? So they didn't give me a number. So equimolar means that they're all what? They're all the same concentration. So let's put 1 mole. It's the easiest one to put. I put a 1 here, a 1 here, and what do I put for HI? Initially I have what? 0. Ooh, no. They said, in this case, they're adding all 3 are equimolar. So they're all going to be the same number, right? Normally they give you the reactants and say you haven't made anything yet. But here they're saying we're going to add 3 gases that are equal, okay? I like this question. So I got this. So there's my initial. Now what's my change? Think with me, party people, okay? We know that this is going to reach equilibrium. And because the K is above 1, isn't the products favored a little bit? All right, so it's going to, right now, K equals 1, but the K was 50. The equilibrium constant was 50. 50 is greater than 1, which means there's a little more products. Right now, this would be a K equal to 1. So we got to show more movement this way. So this is going to go this way, which means this is going to be, changing colors, minus something. I'm not writing X there. Now, hold on. What is this related by? These are both 1-to-1, right? So that's also going to be minus the same amount in moles, correct? Okay, and this you're going to make more of. Whatever this value of x is, it's going to be small, but it's going to go by that. That's going to be the same amount it loses, correct? This is going to gain how much? 1 to 2. Right, so it's going to be plus what? Right. Good job. Do the math. 1 minus x if I was Yoda. 1 minus x. And then 1 plus 2x. So all it means is what? Okay? This is going to increase twice as much as this decreases. Look at your choices now. Okay? More H2 will be produced. Now, forget about the Q. Forget about this Q right here. More H2 will be produced, right? So more H2? No, it's going to go down. It's going from a K equals 1 position to a K equals 50. It's going to go down. So I get rid of that. Okay, more I2 will be produced. No, it's going to move forward a little bit. So it's going to go down. More high will be produced. Yes. We're going to produce more high because we're driving it this way, or no change. So forget about Q versus K. There it is. C is the answer. Okay? I expect you to understand that much. I don't expect you to we're going to do more of that Q stuff you won't see from me. Okay? All right, moving forward. Let's go to the 4C. All right? Or not to be is the question. Okay? Yes. All right, 4C. Here we go. No, I got to stop this. 4C. Come on, show me. That doesn't want to do anything. All right, get out of the way. Stop mirroring. Okay. 4C. Or not to be. Oh, 4C.
Right there.
Thanks. I got a cursor now. All right, here we go. Get bigger. All right, so there's our reaction. Now notice I said copper 1 sulfate. From the summer, you should know that copper 1 sulfate is copper plus 1. You may not know what sulfate is, but you have a reference table. Sulfate is SO4 negative 2. So she'd been able to write those chemical formulas.
Perfect.
Okay, cool. All right. Now, sodium hydroxide, okay, and then we balance. So obviously, if you couldn't get to this formula, you're in trouble, okay? But it's just copper plus 1 plus the hydroxide makes our precipitate. How do I know? Table F. Come on, all right? And so it's really, after all of this is done and said, this is really what happens. Now, who's the limiting reagent? You could have done longhand, or you could have done the moles. And so from molarity equals what? Molarity times the liter, I got the moles. Hey, it's 1 to 1, easy math. In order for all this to disappear, times it by 1, I have to have at least 0.0218. I have more than enough. This disappears. Okay, that's my excess. And if I do my math, it's a 1 to 1. It's plus minus x, okay, plus x, just like we just did. Yes?
This might be a stupid question, but why are they not aqueous if it's only plus 1 and minus 1?
I should write aqueous right here.
So they
Aqueous,
are.
aqueous, and I should. I was bad Grodsky. Okay?
I was just
Did we
wondering.
have to?
No, I won't. That's crazy. Okay? I would say definitely write the phases, but this should be aqueous, solid. Okay, so bad me.
Why do
I won't make that mistake again. All right, please don't find another mistake. I can't handle it. All right. Okay. Did I not do that good? All right. I need to have a little ketchup here too, right? This is performance chemistry. It's not just teaching. Okay. All right. I give you SAD. Was that surprised? I got to work on it. Okay. All right. So moving on. Sorry. Just give us the test. Stop talking. Christmas in July.
It's in the top.
Yeah. All right. Who's the limiting reagent? Excess reagent. Hey, we're going to add the what? Liters together. Oh my God, we haven't seen that before. Okay, how many grams of precipitate we produced? Hey, from the .028 we got from the ice table or the Stoich problems, you got that. This is where people are going to get your stuff wrong. You're going to get your, I can't speak right now, but you know what I meant? Okay? Yeah.
Yes.
This is your precipitate. Who was excess?
So the
Right, so
sulfate.
who delivered the hydroxide, the sodium, right? So if we go back, just to make sure we understand this, to your table, the excess chemical was your, oops, you've got the excess chemical is your copper sulfate. The copper sulfate delivered the copper, so all the copper is gone. No, it's not. So I should have some coppers. But not a lot of coppers because a lot of them got what? Locked up. So I would, to me, there's a little bit of copper left, but not a lot. Who's an excess? I'm sorry, that's excess. The limiting reagent was the sodium hydroxide. Okay? Now the hydroxide's all gone. If you wrote hydroxides floating around, okay, you're gonna get something wrong there. There should be no hydroxides in that container, it's gone. All right, who delivered them? The sodium. So for me, and there's a 2 here, there's a heck of a lot more sodiums than floating around of coppers, right? It's gotta be. A lot of the copper did where? Got locked up. So me, the copper should be the least. Sulfates, they didn't do anything, they spectate, right? But to me, there's more sodiums than sulfates, correct? All right, so that's how I did that, all right? And that's really important. That's almost as important as all the math, because if you can draw that correctly with the right amount, okay? Although I think I have more sulfates written there. Why do I have more sulfates? Maybe because I started with, because it was the excess chemical. So I accept it both ways. I see that, why I was doing this. So I can accept more sodiums or sulfate. I can see why both could be right here, because it depends upon the actual moles. But definitely copper is less than these two. So if you got these switched, I can accept that, I think. I'll think about that. All right. So you guys at home, you can start your test, okay? And I'm going to stop this here.